So we should start now as other participants will also join later. So let me start with the intro. So first of all, a very good morning to the speakers from Third Eye Data and all the participants. I, Aditi Govil here, Senior Executive at Cognizance IIT Roorkee, heartily welcome you all here to the workshop on solving real-world problems with AI computer vision by the Third Eye Data, which delivers end-to-end data and AI solutions for enterprises worldwide by leveraging state-of-the-art data and AI technologies. Third Data has over a decade of experience in transforming enterprises like Walmart, Microsoft, Southern California Edison, British Petroleum, and a host of large and small companies worldwide. So let me introduce to the speakers of today's workshop to you. So we have DJ Das Sir, who is the founder and CEO of the workshop of the Third Eye Data. He started US career working as a software developer in Microsoft and Sable Systems. We have Aprajita ma'am, who is the co-founder and chief delivery officer of Third Eye Data. She has 25 plus years of industry experience. We have Pranab Ghosh sir, who is the chief data scientist in Third Eye Data. He is the owner of multiple open source big data and data science projects. We have Vishal Yadav sir also. We have Vishal Yadav sir who has full stack lead here in the data scientist Third Eye Data company, and Neha ma'am having data scientist lead at Third Eye Data, Ipshita ma'am data scientist at Third Eye Data. We have Pratik Ghosh sir senior data engineer, and Prasanjit sir delivery manager, and Punima ma'am who is the HR manager and coordinator. So I, on behalf of the Cognizance team, welcome the speakers and thank them for providing us with their precious time to enhance our knowledge. So, sir and ma'am, the stage is all yours.
It is my privilege to call upon Mr. Pranab Dash, lead data scientist.
Pranab Ghosh.
Pranab Ghosh, sorry. Mr. Pranab Ghosh for his part.
Okay, let me try sharing my screen. Oh boy. I'm in trouble. It's not letting me share my screen. There is some security. Does anyone know on Mac?
Yeah, I'm on Mac, so maybe then I can share the screen while you can speak.
Okay. Okay. You want to bring up my content?
Yeah, I'm going to share the screen right now.
Okay. Yeah, I thought I went through this here last night, but I probably didn't.
Okay. Yes. I think all of you can see my screen, right?
Yes.
Yes, sir, it's visible.
Okay.
Pranab, carry on, please.
Okay, so welcome everyone. So I'm just going to talk about deep learning as it relates to vision problem. We'll talk about deep learning in general a little bit, and then quickly dive into the kind of problem deep learning solves for vision and the solutions.
Pranab, sorry to interrupt. Would you mind giving a bit introduction about yourself?
Okay. Yeah, I'm the chief data scientist for Third Eye Data. I have more than 35 years of experience. I'm a graduate of IIT Kharagpur and then MIT. I have worked for various companies of various size, worked for most of the big tech companies in the Bay Area. For about last 15 years, I've been working as a consultant. For about last, I'd say 5 years, my focus has been mostly machine learning and AI related problems. I own several open source projects in GitHub. Very active blogger. I blog, once a month. Write some in-depth article. Very active in social media also, LinkedIn especially. Large number of followers, and if you want to connect with me, feel free. So with that about me, let me jump in to what this deep learning is all about. So this is the agenda. So I'll talk about deep learning basics a little bit. So most of the discussions will be at a very high level, conceptual level. I'm not going to go into details of some specific algorithm or get into maths or other technical details. It will be very much at a conceptual level, just to kind of give you a roadmap of what deep learning can do, especially for vision problems. And then some of the cutting edge work that's happening and the future directions. So with that, let's go to the next page. So deep learning, I'm sure, these days deep learning has become kind of synonymous with AI, but it's actually not. So machine learning is part of AI, and then deep learning is I would say, one area of specialization within machine learning. So machine learning is all about, learning from data. Technically, it's called inductive learning. So you're essentially learning patterns from data. As opposed to classic AI, where that there are a lot of activities with classical AI in the 80s and 90s and 70s, essentially involved symbolic logic, and it's kind of top down, whereas machine learning is kind of bottom up. It's all data driven, inductive learning. So deep learning is a kind of machine learning solution. It's inspired by the architecture of our brain, although we shouldn't have any illusion about deep learning networks being comparable to the complexity of the brain. It doesn't come anywhere close. It solves many practical problems. That's one thing good about it, but it shouldn't be associated with human level intelligence or human level cognitive skills, although a lot of people make all kinds of claims, but it's just false. It's a very powerful engineering tool. Essentially, it performs statistical correlation in very high dimensional space on large amounts of data, which you cannot do with any other technique. So that's where its real power comes from. And it solves many real world complex problems which cannot be solved by any other technique, especially suitable for any kind of natural data, higher dimensional natural data. For example, vision, audio, then language, video. So that's the kind of data where deep learning really excels. If you have regular business data like tabular data, deep learning is probably overkill. You probably don't need it. It's really shines with very high dimensional, natural data, and most of the applications are actually with those kinds of data only. All right, next one. Next slide, DJ.
Yeah, Pranab, I will have Prashanjit share. So I'm going to stop sharing and Prashanjit will go on the next slide. So
Sure.
Prashanjit, over to you.
Sure, absolutely.
Okay, so next one. So some terminology. So in our discussions, we'll be often making reference to various kinds of networks, and these are the acronyms. MLP is just a regular feed forward neural network. CNN is convolution neural network. It's used mostly for image problems, although there are some applications for text problems also. RCNN is a special kind of convolution neural networks where you want to identify multiple objects within an image. R stands for region. So essentially, it identifies the bounding box as well as the object within those bounding boxes. And there could be multiple of those in an image. RNN is a recurrent neural network, mostly used for sequential data, like language. Language is sequential data. LSTM is similar to RNN, but more sophisticated. Actually, RNN came first and then came LSTM, and even LSTM has been kind of superseded by something called transformer. Then GAN is generative adversarial network. This is something very unique. Most of the networks that we see here, they are all used for predictive task or where you want to make some kind of inference. But GAN is a kind of network called generative network. They essentially, their job is to generate data. So all these fake videos or fake images that you see on the internet, they are generated by this kind of network called GAN.
Okay.
So anyone has any question? Okay, sorry. Then transformer is something very recent. It can operate on, actually it started off with being applied for language problems, but it's gaining ground for vision problems also. So it's slowly replacing convolution CNN for vision problems. And those networks are called vision transformers anyway. So it's kind of the state of the art in deep learning right now, transformer. I don't know if you have had this news this week, the big news, deep learning news. One was a language model from Google called, what is it called? Anyway, I forget the name. Anyway, and then there is a vision model from OpenAI, and they're both based on transformers. The vision, vision generative. So you can kind of create an artificial artworks from OpenAI. It's called Del.E. That's the product. So they are all based on this transformer, which is a kind of network. Anyway, let's go to the next page. So as I said, it mimics brain somewhat, but in a very simplistic way. It doesn't come anywhere near the complexity of brain architecture. I actually spent, out of self-interest, I spent a number of years studying the architecture of brain and neuroscience and all that. It's really fascinating. So it doesn't come anywhere close to that, but it's a very simple-minded, model of brain. So essentially what you have is you have layers of neural units and they are connected. So each layer is connected to the previous layer. It takes input from the previous layer, does some processing and then passes the data to the next layer is the input. So you have multiple such layers, and then at the output of the final layer is the output of your network. So the input is fed at one end, and at the other end you have output. So for example, if you want to do image classification, the way that will happen is you will have a CNN network. Then your raw pixel data will go as input to one end of the network. And at the other end, let's say you want to do some classification, and let's say you have 10 different kinds of objects you're classifying. So there will be 10 outputs at the other end, and each one will have, it'll output a probability value. So whichever output has the highest probability value is the corresponding label is the label for that particular image, or in other words, that is the prediction for that image. So you may have images for, let's say, 10 different kinds of animals, So there'll be 10 outputs, and each one will have a probability. So you just pick the one with the highest probability. So that's your output prediction. So as far as math goes, all these networks are essentially, lots of matrix transformation, linear algebra, because the output of one layer goes through a matrix transformation, and it becomes the input to the next layer. Actually, after the transformation, it goes to something called a nonlinear activation, and then that becomes the input to the next layer, and so on and so forth. So it just, keeps repeating. So that's the, at very high level, what the deep learning networks do. And most of the layers in the deep learning model, most of the layers are essentially doing feature engineering. So they take some input. So for example, for image, where you feed in, raw pixel data, as the data gets processed through different layers of convolution, it extracts higher level features of the image. So it might extract some line, it might extract some shape. If it's an animal, maybe the shape of the ear, or the shape of the head. So it keeps extracting higher level features. So what the network is doing essentially is, most of the network is busy extracting all these features. Then at the very end, it makes some prediction, based on very high level features that it has extracted. And it works the same way, whether it's image or whether it's text, whether it's audio. Essentially, that's what it does. It does a lot of feature extraction or feature engineering in most of the layers, and then at the very end, it makes some kind of a prediction. All right, next one. So this kind of network, if they have at least one or more hidden layers, they can approximate any function. So that's why this deep learning networks sometimes are called universal function approximator. So you can think of that as a function approximator, just like you do linear regression, except that this is happening at a very high dimensional space. But the basic operation is some kind of function approximation. And so what happens is, so the data flows, there are two flows. One is forward and backward. So it flows forward, and then at the end, when you get the output, and then we have a network output, and then we also have the actual output that we know, because we have some training data with some level, right? So the difference is the error. So what happens next is that error is actually flowed backwards towards the input, and that error is propagated, and the network weights are updated, based on the error value. So that's essentially the learning process in deep learning. And this process of the error, flowing backwards, it's called back propagation. So that was a major breakthrough in deep learning technology, this back propagation and how to propagate the error to adjust the weights. And that has an analogy to human brain, where the synaptic connection strengths, they get adjusted as we learn, as we grow, and as we learn. The same thing happens in our brain also. Although the mechanisms are not identical, but something similar happens in our brain also. All right, next one. Next one. Okay. So, so what are the different learning tasks in deep learning? So the most common one is called supervised learning, where you have some data and you have some label for the data. For example, you have an image, and then the label is what kind of image it is. For going back to the previous example, which so the label in this case might be the what animal that image is for. And so essentially it's a because you have this label, it's called supervised learning, because we are providing that label, and based on that the network learns. In unsupervised learning, we don't provide any labels, and the goal is not so much prediction, it's learning about patterns in the data. And there are many usages of unsupervised learning. So in classic machine learning, for example, clustering is a unsupervised learning technique. In the deep learning world, one example of unsupervised learning is something called autoencoder. So the way that works is that you have some input, and you want to learn some internal representation of that input. So that input goes to a network called encoder, and that encoder output goes through another network called decoder. And the decoder is supposed to be able to reproduce the original input. That's the goal of the decoder. So that's unsupervised learning. In self-supervised learning, it's similar to supervised learning, except that there's no label, but it will use part of the data as the label. So for example, in many language tasks with transformer, what they do is they'll take some text and they'll mask some of the words in the text, and then train the network to predict that that particular word that has been masked. So this kind of learning is called self-supervised learning, where we are not providing any label ourselves. The data kind of learns from the data. And this is extremely powerful in deep learning. It's used a lot. Most of the language and vision deep learning models, they all use self-supervised learning. So for example, there is a pre-trained language model from Google called BART that uses self-supervised learning. It's extremely powerful. All right, next one. So these are some of the tasks, vision tasks in deep learning: the image classification, then identifying multiple objects in an image, image segmentation, image generation, image caption generation, which is basically given an image, it will generate the caption for the image. Then image generation from text. So you provide some text, and so for example, you say dog, and you provide the text, this is a dog, and it'll generate an image for dog. In fact, the deep learning model that I just mentioned about, called del.e from OpenAI, it was I think they announced a few days ago. So that's what it does. And it's pretty impressive if you look at some of the images. It's all over the internet, actually, last few days. Then image anomaly detection is detecting anything unusual in image. So that has a lot of interesting application in medical and few other fields, manufacturing. So these are some common, vision tasks, that can be solved by deep learning. Let's move on. Object detection is we have an image and we want to classify the image. We talked about it. So there's a CNN network with multiple convolution layers, followed by a dense network, which is a regular feed-forward network, which does the final classification. So the convolution operation is nothing but it's like a filter, which operates on a patch of image, rectangular patch of image, to produce feature values, and then those values they go through a nonlinear activation, typically or rectified linear unit ReLU, and then that output goes to a pooling layer, which is essentially downsampling, and then that final output becomes the input for the next layer. And this convolution filter weights are learned through training. So again, this goes through that back propagation, and typically training involves taking some data and then creating multiple batches out of the data, and then feeding the batch repeatedly and over again through the network. So each object in that batch, it forward propagates through the network and then backward propagates, and then while it's backward propagating, the network weights are updating. So in typical training process, you track the the error, and when the error goes below some acceptable level, you decide that the network has been trained and it's ready to be used. All right, next one. So here, the task is a little bit more fine-grained. So your image may have multiple objects, and this is the kind of stuff that Third Eye has done for SCE, and then Vishal and others can go into the detail. So they use something called RCNN and various version of RCNN. So as part of the training, you have to annotate all the objects with their bounding boxes, and also you have to annotate what kind of object it is within the box. And then you train the model. And after it's been trained, and then so for each bounding box, it will make it will actually do an image classification. And then once it's trained, then given an image, it will tell you what the different objects are and the corresponding bounding boxes. So some of the popular model is RCNN, and then FRCNN, which is faster RCNN, and then there is something called YOLO, YOLO. So these are all for detecting multiple objects along with their bounding box, which is the bounding rectangle. All right, next one. Image segmentation is even more fine-grained. So basically, it's almost like there are multiple objects in the image, and for each pixel, you are predicting what object that pixel belongs to. So this way, you can get the outline of the objects in the image. So it's even more powerful than multiple object detection, because it actually detects the outline. So the network, it actually consists of an encoder and decoder. So the decoder maps the encoder output to object outlines. There are different kinds of segmentation. In semantic segmentations, you just classify the pixels. And so essentially you predict what class a pixel belongs to. Now, sometimes you may have multiple instances of a class, and in that case you need instance segmentation. So for example, in an image you may have two cars, right? So instance segmentation will identify, for any given pixel, it'll tell you which object, which instance of the object it belongs to. So it's more powerful. And panoptic segmentation is a combination of both. It'll, for each pixel, not only will it classify what type of object, but also which instance of the object that it belongs to, if there are multiple. So it's a combination of the previous two. Typically, the networks that are used for image segmentation is RCNN and CNN. Yeah, so that's what image segmentation is all about. Sometimes it's called scene understanding. So it's like you're trying to understand if there are various objects in an image, you're trying to understand their semantic relationship. Okay, next. Image generation. So these kind of models are very different from what we have discussed so far. So everything we have discussed so far, their job was inference or prediction. So this one is unique in the sense that it actually generates data. So the task is generative instead of predictive. And so there's a lot of fake stuff that you see on the internet. They are generated by this kind of network, like fake video or some fake image. And so it consists of two subnetworks. One is called a generator, the other is called a discriminator. Now for image, what the generator does is that it tries to generate realistic images with you give it some random noise and it'll generate some image. And the job of the discriminator, which is the other part of the model, is to discriminate between real images and fake images. So the discriminator takes real images as input. As training goes on, the generator learns to generate more and more realistic images, and the discriminator learns to how to discriminate better, between real and fake. So this kind of training is based on game theory principles, as if the discriminator and the generator are two involved in a two-player game. It's a very interesting idea, and so there's a guy called Ian Goodfellow. He is one of the deep learning experts. So he came up with this. It's very powerful. So most of the there are a lot of content generation that's done uses this kind of network. All right, next one. Cross-modal generation. So this is even more powerful. So what it can do, for example, image captioning. So given an image, it can generate caption for you. And obviously you have to train with lots of images and lots of real captions. So it also uses a encoder-decoder pattern. And the networks that are used are CNN, RNN, and LSTM. So the reverse task is given and generating an image, given some textual description. So so this can use the GAN network. So the generator input in this case will be some kind of text embedding with some noise. And the discriminator input will be text and the corresponding image pair. So that's what this model that I was telling you about, that this was announced this week, that's what that does. DAL-E. Given some textual description, it can generate art form, all kinds of artwork, paintings. So this kind of generative models are called cross-modal because there are multiple modalities. There is image and there is also text. So that's why they're called cross-modal, generation. All right, next one. Image anomaly detection is also, it has a lot of, practical usage. For example, medical diagnostics, Like someone might be taking some X-ray of the chest, and if there's anything unusual, that might be indicative of some medical problem, right? So that's an anomaly because the X-ray will be different from normal X-rays. It can also be used for defect detection in manufacturing. So this is where the autoencoder, which is a unsupervised deep learning model, can be used. So the way it could be used is that, remember, the autoencoder is it has a encoder and then it has a decoder. So, and in this case, both the encoder and the decoder will be based on CNN. So what the encoder will do is that it will take an image and it will generate high-level features from that image, which is the encoder output. And the decoder will take that as input and it will try to regenerate that image. So whatever is the difference between the regenerated image and the original, that's the error. So that's the error that gets used to train the model. So if you have trained this kind of autoencoder and CNN-based model with lots of, let's say, normal images, then you feed in some image with some anomaly, like some chest X-ray or some, picture of some manufacturing parts. What will happen is that once you feed it through the network, the difference between the regenerated image and the original image will be very high because it's not something the network has encountered before, right? Because it's different from all the normal images that you use for training. So when that regeneration error is high, you know that there's something unusual in the image. So that's how anomaly is detected in images with autoencoders. GAN also can be used for anomaly detection based on the difference between the image and GAN generated images. So you can generate lots of images to the GAN, and then if you find any significant difference between those images and your image with an anomaly, you know that there is something unusual about that image. But autoencoder is generally used, but there are some solutions based on GAN also. Okay, I think that's as far as the different vision tasks. Let's see what the next slide is. Oh, transfer learning. So these models are extremely expensive to train. I mean, it might take, if you have to train them from scratch, it might take several days, running on some GPU cluster in some cloud somewhere, right? And it might cost like, millions of dollars to train this model. So it doesn't make sense for everyone to train this model from scratch. Fortunately, some of the big tech companies, they have trained these models and they have made them publicly available. So, and actually, Thought-I has used one of those trained models, but you cannot use those models as is. You have to do additional training. So you take one of those models, and what you do is for your particular domain specific data, you do additional training, except that during this training, you train only the last few layers of the model. Sometimes, the very last layer of the model, and you freeze all the remaining layers. So this is called fine tuning. So although the model is already trained, but it's not trained for your particular domain and your particular kind of images that you have, right? So this additional training is necessary. And without transfer learning and pre-trained model, I mean, it's almost impossible to, unless you are a big company with lots of a lot of money and a lot of resource. Most people cannot afford to train this model from scratch. So I mean, so essentially they will be out of luck. They won't be able to use deep learning models without this kind of pre-trained models, that are available for free. So different companies, Google, Facebook, Microsoft, they all have made available, all kinds of, pre-trained, models for people to use, and they're for free, just like open source code. Okay, next one. So this is a very interesting topic, although, like I said, the CNN is inspired by human visual processing, but the human visual processing is actually quite a bit different and a lot more complex compared to the simplistic, CNN model, where you just feed in some data and the output, you get the output at the other end. The human visual processing is a lot more complex. It's bidirectional. It's based on a lot of knowledge you have about the world. So way it works according to neuroscience is that, yeah, I mean, there is the visual signals from your retina of your eyes that gets processed just like a CNN model, but at the same time, higher up in some area of your brain, there is a generative model which is always trying to predict what your eyes might be seeing next, and based on the prediction it will actually generate some signal. So that's like a generative model. So there's one signal that's coming from outside in through your eyes, and then there's other signal the brain is pushing down through the network, which is the anticipated signal. And so ideally, they will be same, but they may not be. So whatever the difference is, the brain uses that to learn and modify the network. So it's very much different from the simplistic CNN model for image processing, a lot more complex. For one thing, when brain generates that signal, it's based on some knowledge about the world, right? So for example, if you see some moving object, it know that your brain knows that it has seen that object, and then let's say it kind of knows, in next 10 seconds, what the object might look like. So based on that, it will kind of make a prediction and generate the signal, which is a lot more sophisticated than what happens in CNN deep learning models. So let's see what's next. So these are some articles that you might be interested in. I mean, I focused on articles that are easy to read. These are not really academic papers, but if you go into these articles, there will be reference to the actual paper, which will have a lot more, technical content, a lot more details about all these solutions. So you can follow up, and if you're interested, you can, read up on those too. But these are all articles and blogs, essentially, that I have. Is there anything else? Is that the last slide?
Yeah, I think this is the last slide.
Okay. All right, I'll end there, and thanks everyone for joining. Hopefully it was useful.